Okay, welcome back. We are today working on lesson 6.4. So, of course, on the bottom of your note sheet, you should be writing down the objective, which today is student will be able to solve systems using any method, meaning graphing, substitution, elimination, right? And recognize what are called special cases of systems. So, today we have a guest appearance, and I will know whether you actually watched this video if you can tell me the names of these two knuckleheads. One, him, and two, him. All right? So you have to be able to tell me who that is, and that way I will know whether you watched the video. Get a little closer so they can see you guys.
I'm getting closer.
Well, I'll give them your names. You just have to be able to tell me. T-Mac and Dr. Love. T-Mac, Dr. Love. All right. So here we go. You guys hopefully have gotten down the... Thank you, gentlemen. You can return to your seats. And the rest of us, yes, they're getting a standing ovation here from their class. But you should be writing down the objective, and we need to get started on this. So let's look at this. Now, over here on the background section, you will notice that I have a brief summary of the three methods for solving systems we worked on. Graphing, substitution, and elimination. All right? And then down here are some notes that we need to fill in. What are these special cases he's talking about here today? All right, so let's look at it. I got a little mark here I want to erase. But let's look at this first system, all right? And when we solve by graphing, we graph both equations, and we look for where the lines intersect. So let's look at this first one and ask ourselves, what form is it in? Well, it's in, and I'll make it a little bigger here. This one is in slope-intercept form. So the y-intercept is -1. I'm going to plot that. The slope is 1, so I'm going up 1, right 1, 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 up 1, right 1. And continuing that pattern, all right, it's going to allow me to graph a really straight line. So there's that line. Now we need to graph the other one, and we need to find the point of intersection. That way we will know the ordered pair that solves the system. So graphing this one, I may notice that, wait a minute, this one actually isn't in slope-intercept form. It's in standard form, which I like to emphasize is all about the intercepts. So when x is 0, y has to be 2, and when y is 0, x has to be -2. So how do we graph those? Well, 0, 2. That is right there, and -2, 0. That's right there. Now, to graph more points to get a nice straight line, I may ask myself, if I go up 2, I go right 2. So I can continue that pattern. Up 2, right 2. Up 2, right 2. Up 2, right 2. Up 2, right 2, etc. Now I can graph that line. And it turns out that I am looking for... Oops, I got off there a little bit. Let me correct that. So... should have been right there. Now, got to be careful when you're graphing. Even your teacher has to be careful when you're graphing. Now, the question is, I'm looking for where these two lines intersect. And we can see that they don't. And if we actually examined their equation, we would find that they have the exact same slope. The slope of both of these lines is 2. But they have different y-intercepts. Now, you'll remember from Unit 5 that same slope, different y-intercepts means they're parallel, so they never intersect. So this is a special case of a system in which there is no solution. There is no value that makes both of those equations true. Now, we can see that pretty easily graphically, but we also need to look at what does that look like when we solve this system using an algebraic method, meaning substitution or elimination. So let's try it. Let's write down our original problem again. Y equals x minus 1. And here, -x plus y equals 2. Now, if we're going to use substitution, we already have a variable alone. And I meant to highlight that. So we already know that y is the exact same thing as x minus 1. So, if we're going to combine a couple pieces of information here, we're going to say to ourselves, let's take this piece of information and this piece of information. So, -x plus, and now I'm replacing y with x minus 1, because y is the same thing as x minus 1, and that equals 2. So that's the second equation with y being replaced with x minus 1. Now if I solve this, -x plus x is 0. So I end up with -1 equals 2. Oh, wait a minute, our variables disappeared and we have a false statement. Our variables disappear and we have a false statement. So let's actually try this using elimination. All right, maybe something went wrong there in that method, and we want to try and solve this using elimination before we make any conclusions. So if we write down our original problem again, y equals x minus 1 and negative x plus y equals 2. Now, to remember to use elimination, we want to line up our x's above our x's. So I'm going to choose to move this x to the other side of the equation, making this negative x plus y equals negative 1. And this equation stays the same. Now, I want to add them together. That's what you do in elimination, and you want to add them together to eliminate a variable. So, do I eliminate a variable? No, I wouldn't eliminate a variable. Here I would get negative 2x, and I would get positive 2y. So, I need to adjust one of the equations. I really wish this coefficient was positive 1, so I'm going to multiply this entire equation by negative 1. That's going to give me x minus y equals 1, and this equation stays the same. Now if I add the two equations together, x plus negative x is 0. Negative y plus y is 0. So here I get 0 equals 3, which again is a false statement. Now, our answer to these systems isn't false. We know from looking at the graph that our answer is no solution. So we need to learn to interpret this. We need to take these notes over here. So, no solution is a special case. Substitution elimination, your variables disappear and you have a false statement. So, when your variables disappear and you have a false statement, you interpret that as no solution. So our answer here, just like in the graphing method, is no solution. Now, that's not the only special case we have to look at. So, if you'll work with me here, and we want to go to the next page, let's try this one by graphing. Well, I'll make it a little bigger here. If we're trying this one by graphing, y equals 2x plus 1. The y-intercept is 1, and the slope is 2. So up 2, right 1. Up 2, right 1. Up 2, right 1. Up 2, right 1. And now this one, it isn't in any form that we may recognize, but if I move this to the other side, we could say, aha, that's in slope-intercept form, or standard form. Or if I move this to the other side, we may say, wait a minute, now it's in slope-intercept form, which might be easier for some of you. So if we leave this as 2x plus 1 equals y, because we moved this y to the other side, then we now see that if we're going to graph this line, we finished graphing that line before, that this line also has a y-intercept of 1 and a slope of 2. So if I graph this one, wait a minute, it turns out they're the exact same line. So remember, our intersection, when we're using graphing as a technique, is where the lines intersect. Well, where do these lines intersect? They intersect at an infinite number of points. So our answer is actually infinitely many solutions. Right? That's actually our answer. And the key thing we want to recognize here is that that is not the same as saying that everything is a solution. You can't say all real numbers, because here's an ordered pair that doesn't solve either equation. Here's an ordered pair that doesn't solve either equation. Here's an ordered pair that doesn't solve any equation. It just means there's too many solutions to count. There are infinitely many solutions. And now, quickly, we want to look at what does this technique look like when we're actually using substitution or elimination. Now, remember when we did parallel lines, it turns out our variables disappeared and we had false statements. Well, let's look at see what happens here. So let's write down our original problems again. And you'll notice that we are pretty well set up to use substitution. Y is the same thing as 2x plus 1. So I'm going to come over to this equation. And I'm going to replace y with 2x plus 1. So I get 2x minus, and now I'm replacing y with 2x plus 1. I still have the plus 1, and it equals 0. Now if I solve that, I get 2x distributing the negative minus 2x minus 1 plus 1 equals 0. Combining like terms, I get 2x minus 2x is 0x's, so those go away, and negative 1 plus 1 is 0, so I'm left with this, which is a true statement. So, in terms of our special cases down here, all right, what we want to summarize our notes as being here is this, is when we have infinitely many solutions. We just saw that by graphing, it turned out they were the exact same lines. But we also want to summarize what happens using substitution or elimination. Your variables disappear, and you have a true statement. Now, I want you to finish up and do the same problem using elimination and make sure your variables disappear and you get a true statement. Plus, it's a way for you to practice the elimination method. So, come into class prepared. Be able to tell me who those two characters were. I'll give you one more look at them if they'll get over here. Here they come. He's coming slowly. He's coming far too slowly. Again, so if you can't tell me who these characters are, then you didn't watch the video. T-Mac, Dr. Love, both in the house. See you next time.